So let's talk about another equation that's used for a very similar purpose. It's Manning's equation, and it's basically another hydraulic equation, but it's a different formulation of how to relate depth, cross-sectional area, and the flow at a given location in a channel. So the left side of the equation is the same. It's giving you the average velocity of the water, but the right side of the equation is different. We have K, which is a dimensionless constant. We have N, which is Manning's roughness. That's a dimensionless, similar to the friction factor, it's a dimensionless number. R is again the hydraulic radius, same idea as the hydraulic radius before, and S is again the energy surface of the water surface. So we can go back to Word. I'm going to hit Alt equals to create a new equation. I'm going to go through the same steps here for my average velocity and my equal sign. I need a K over N here, so I'm going to go ahead and create a fraction, K, N. I'm just using the arrow key to move around, the arrow keys to move around in the equation, by the way. I find that to be the fastest way. I have a hydraulic radius. In this case, the hydraulic radius needs to be raised to a power, and that power, oops, jumped around a little too much there. That power is a 2/3 power, so I want to create a fraction, put 2/3 in there. My slope, again, that's going to be raised to a fractional power. In this case, it's the square root, or the half power of slope. So that's Manning's equation. Again, the idea here is to go through a dimensional analysis. That K is going to be dimensionless. So we can put in square brackets and put a 1 there. That N is also dimensionless. Put in a 1 there. That radius, and I'm going to leave that power there, so what I want to do is I want to put in parentheses here. And remember, the hydraulic radius is the cross-sectional area over the wetted perimeter, so I need a fraction here. And to save myself some work, I already have this right here, so I can do some cutting and pasting. And likewise, I can put a 1 in for my slope. And finally, again, I can cut and paste because I know that this velocity is going to have the same dimensions as the velocity in Darcy-Weisbach. Okay, so I have my setup. Now I can do my simplifications. Start on a new line. Well, I recognize that all of these 1s go away. Then I can start working on those lengths. Well, length squared over length is just a length, and then I end up with length to the 2/3. Which I could represent in a couple of different ways. I could just say length to the 2/3 power, or for whatever reason, if it made more sense, I could say length to the 2nd power times length to the -3rd power. And remembering that italics are a no-no when it comes to dimensions. So clearly this doesn't work out. We don't even have time on this side of the equation to give us this length per time for the velocity on this side of the equation. So this Manning's equation is not dimensionally consistent. As a matter of fact, that k also depends on the units. So the way that they get around making n be the same Manning's roughness, no matter what system of units you use, is to say, well, you need to use a different k depending on the unit system that you're using for r, s, and for the resulting u. So this is a good example of a non-dimensionally consistent equation. That means it was derived more from patterns in data necessarily from theory. Now that doesn't mean there's no theory behind the equation. Don't get me wrong there. That's not true at all. There is very sound fundamental theory underlying setting up the empiricism this way. However, this equation by itself does not exhibit dimensional consistency and is more evident of an equation that's been derived by patterns observed in data. So these are a couple examples of what I expect to see in the homework and an example of what I mean when I ask you what dimensionally consistent is and what that means in terms of whether that equation likely came from theory or empiricisms or not. So hopefully that gives you an idea of what I'm looking for in the homework assignment for this particular lab.